Thank you very much. It's a huge honor to be here. Today I'm going to talk about the information measure estimation and how to have some magic procedure to boost your sample size from n to n times log n without conducting any more experiments. It may look weird, but later hopefully you'll be convinced that it's exactly a right description of our results. It is joint work with my lab mate Kartik Wenkart and Yanjun Han, who is still an undergrad in Tsinghua EE, but he's interning in our lab. He's so good, actually, we are now working for him. And my advisor, Sahi Weissman, Stanford, who was supposed to be giving this talk, but later we decided I'm going to come first to whet your appetite. What's the question? We start with the simplest one. Suppose I observe n samples RID from a discrete distribution P with support size S, but I don't know its size. But I don't care about that size. I care about these two functional or two class of functionals. The Shannon entropy, of course, is very important in information theory, and also I care about this function f alpha, defined to be summation ph alpha, any alpha larger than 0, has got many interpretations, and also if you take a log and normalize a little bit, it's going to be the linear entropy, which Himanshu will talk about later. So we're interested in this not only because they are interesting in practice, and also because they exhibit different levels of smoothness, because this functional each have a sort of a non-smooth point at 0. We want to see how the estimation problem's difficulty varies according to level of smoothness. So this question is very fundamental, and it falls into general realm of questions where you observe some samples from certain distribution parameterized by certain theta, here is P, but you don't care about theta, you care about the functional. So we need to first go to statistics literature and see what is known about that. We start with Shannon entropy, thanks to Kartik for suggesting this picture. Then the most ambitious question we can ask is that I want to ask Shannon entropy. I give you n samples, what's the optimal estimator? However, you go to statistics literature, you will find that in finite sample theory, there's no consensus on what is optimal. There are many of them, but unfortunately for this problem, it's even worse. For none of them, we can compute the optimal estimator. So basically, we are really screwed up in the finite sample, but actually it's well known in finite sample theory. If you ask a statistician, and he will tell you in general it's hopeless. So it has been at least observed 50 years ago that we need to go beyond this. We need to go to asymptotics. So we ask a question. Suppose what I want is the optimal estimator for entropy when the number of samples go to infinity, when by the problem size S is fixed. What's the optimal estimator? This problem is also non-trivial, but now it's already classical. It's in the textbook. We define the quantity called empirical entropy, HPN, where Pn is an empirical distribution. And Pi hat is simply the empirical frequency of symbol I. In other words, it's basically evaluate the entropy functional at the empirical distribution. It's basically plug-in approach, can be shown to be maximum likelihood estimator, seems to be quite good. Actually, we can show to be quite good. So using the modern asymptotic theory, we can show that its estimator is really good in asymptotic sense, even in the constant. So we can never improve it, even in the constant, in the asymptotic sense. So it seems we can just go home because we can show it's already extremely good, given these extensive efforts. However, there's something missing. If you recall that we have actually completely given up in the finite sample theory, and we have got something works really well in the asymptotics. Then what about I use MLE when n is finite? If it is also very good in some sense, then we can also go home, because this is what we actually use every day. There's nothing to improve. However, the sad news is that in general, we're going to show for a large class of problems, including all of them we discussed, it's going to be a really bad idea. It's bad to the extent that if you use this in practice, probably your application will completely diverge. But actually, if you use the best one, it's going to converge, and the gap is really big. So hopefully it's going to be interesting. And before talking about our optimal schemes, we need to discuss our evaluation criterion. We use the standard statistical decision theory framework. We denote by MS all distribution with support size S. We define the quantity called the risk function. Supposing estimate ft, I use f hat. The risk function of f hat is defined like this. We define the quantity called the maximum risk, which basically is a maximized risk function over all possible distributions supported on S elements. That basically quantifies what's the worst case performance of my estimator. And I also define the quantity called the minimax risk, which is the maximum risk you infimize over all possible estimators. In other words, it quantifies what's the minimum possible worst case performance I can achieve. And what I hope is that the maximum risk of our estimator is going to be at least close to the minimax risk, and then we should be really good in this criterion. We use the following notation to quantify these two constant sequence, and now we are going to start analyzing this. So before we start to construct the optimal estimator, probably we need to analyze MLE. But otherwise, how can we know how to improve that? So in order to analyze L2 risk, as Yihong suggested, we need to analyze both bias and variance. Now you recall statistics 101. The bias is defined to be the functional minus expectation of your estimator, and the variance is simply the definition of variance. What about the MLE? Then we compute that. We compute non-asymptotically the maximum risk of MLE in estimating entropy, and there are two terms, as we said, squared bias and variance. And actually, it is very interesting to us. Because let's think, if you fix S, let n go to infinity, you'll only be able to see the second term, because the first term vanishes at a rate in n faster than 1 over n. However, if n and s may grow together, actually the first term will dominate, because the first term will not vanish if n is smaller than s, but second term will easily vanish if n is larger than log s squared. So then we make a conclusion. In general, for this problem, first of all, s is the threshold for consistency. Second thing, that the bias actually is dominating. And we need to reduce bias, or we give a theorem showing it's impossible to reduce bias. It's what we are going to do. So, but this problem is also extremely fundamental in statistics, because whenever statistics estimation, we want to either consider the balance of bias or variance. So let's first review what we know about reducing the bias, the general approaches. One idea you may come up to mind, which is Taylor series. Right, I have HPN. What about I do Taylor expansion of HPN around the true point P, compute certain expectations, and cancel certain terms, correct certain terms? It was tried in 1950s and shown by Panitsky that does not work. It requires still S samples. Bad idea for this. And there's also an idea called jackknife.
You don't know P, right?
But this idea, you correct that, but you plug in empirical distribution into that P. That's the general idea of Taylor series expansion. You can expand, but you correct using your unknown estimate. The idea called jackknife seems to reduce the bias in a asymptotic sense, however, shown by Panitsky not to work in this high-dimensional setting. Bad news. There's also an idea called bootstrap. It's called bootstrap bias reduction. However, it's also a resampling technique, really interesting statistical methodology, and we recently showed also does not work. Really disappointing. But we don't give up. We also think the idea called Bayes estimator. So what about we first design a prior, and we compute the Bayes response with its conditional expectation under that prior. Probably it will have good frequentist properties. We computed that, and also does not work. I still don't give up. I think of another idea, which is what about I first use the Dirichlet prior to smooth the distribution, so-called Laplace smoothing. Then I plug in the entropy functional, and we show it also does not work. It's really bad. Actually, there are many more in the literature. I'm not exhausting all of them. So it's really frustrating. We look at this question, but later there is a recent breakthrough by Valiant showing that the exact phase transition for entropy estimation is S over log S. It means that it suffices to take n much larger than S over log S to achieve consistent estimation. Now, all the methods we analyze, but some of them are hard to analyze, cannot do it. But we look at slightly at detail at their approach. They essentially have two ideas. One idea is based on linear programming, really cool idea, but has not yet been shown to achieve the minimax rates. In other words, in CS term, it's called dependence on epsilon. It means that although I know n much larger than S over log S, it's going to converge to 0, but how fast is not clear. Second thing achieves this, but only works for n not too big. But we want to make sure that whenever my n S is, I want it to be optimal. And also, it's not clear how their approach can achieve minimax rates for other functional, such as the F alpha we consider, because we also think, as a general mathematical theory, we should be able to deal with very large class of functionals. So we ask a very ambitious question. We would like to find a systematic methodology to improve MLE, achieving minimax rates for very wide class of functions, and we think it might be easier, actually, than dealing with only a single function. We have to say this problem is still widely open, but later we're going to discuss what we have done. So we are thinking about the reason why Taylor series fails. The reason why bootstrap jackknife fails. We think the reason why it fails is that, first, Taylor series fails because Taylor series is a local expansion idea. We know that Taylor series only quantifies a functional in a local sense, but our question is a minimax estimation. We take the worst case over all possible cases. So it's very uniform criterion, but you use a local technique. So in some sense, it's not really compatible with the criterion. The reason why bootstrap and jackknife may fail is that they are so generic ideas. We proposed a really hard minimax estimation problem, highly dependent on the functional. However, if that works, it means that some generic idea without considering the functional form f suddenly miraculously succeed. We think that's too good to be true. So probably we think you start with first principle. Consider simplest setting. Since we want to reduce bias, what about I write down the expression of bias and see what it looks like? So I take the simplest case, x binomial random variable, which means s is 2. Suppose I use whatever estimator gx to estimate fp. I write down the bias is nothing but this. And we found that suddenly we can draw two conclusions. The one conclusion is that only polynomial with order no more than n can be estimated without bias. Because but 0 bias just means this bias is 0 for all p, but that immediately implies fp equals that guy, but that guy is a polynomial with order no more than n. Second thing that the bias actually corresponds to a polynomial approximation error, which means that probably if you want item to reduce bias, it suffices to design the polynomial g such that it approximates that fp really well. This idea actually not proposed by us. In 2003, and Paninsky proposed to try to solve this problem. Suppose try to minimize this supremum of a bias g and try to find the polynomial g, try to find the coefficient g such that you can minimize that, because that's essentially the minimal bias you can ever have. And unfortunately, it does not work. It's very disappointing. We feel this idea is so good. How can this not work? But later we thought that there is a simple reason explaining why it does not work. Because let's remember, at the beginning we said, Hayek and Lacan told us as n go to infinity, MLE is really good. It means that when n goes to infinity, whatever estimator you give me, it has to be similar to MLE, which is similar to plug-in. However, will that scheme as n goes to infinity give me something similar to MLE? It is not very clear as actually we can show it's far from it. So basically, it simply has violated already existing conclusions in asymptotic statistics, so it's destined to fail. But then we think the idea is still very good, because it clearly captures what is a bias. And the best polynomial approximation has been introduced by Yihong, and it's basically the polynomial that minimizes the maximum deviation function and then that polynomial. Here's our approach. For all the functionals we consider, we decompose the region into two. For each empirical frequency p a hat, if p a hat is smaller than log n over n, we declare you're operating in a non-smooth region. Because for function we consider p log p or p h to alpha at 0 probably is non-differentiable or is not infinite times differentiable. We think it's bad, and we replace that functional. We simply throw that functional away. We think this functional too bad. I replace that by the polynomial, so that functional just disappeared. We replace it by a polynomial with order log n. Then we apply unbiased estimate of that polynomial, because as we discussed before, any polynomial with order no more than n can be estimated without bias. We estimate that. For that part, smooth is easy. We simply plug in actually, but it turns out you still need to do certain correction, which is something we are still trying to understand now. A simple methodology we apply to any function we considered, and turns out to achieve the maximum risk, the best results. But you may ask me the following question. I understand that you need to cut the threshold, because you think your functional, the problem of the bias mainly contributed by the point near 0, but why is the cutoff log n over n? I understand you need to do approximation, but where approximation log n? This stuff, but you need to understand this to do it. It is a paper by Sergei Bernstein in 1938 on best approximation certain function. We need to use this hardcore mathematics to finally solve this. Here it's time to acknowledge that these ideas really inspired by pioneers in the field. Probably the final pioneer is a paper by Lepsky, Nemirovsky, and Sponkin in 1999, who used the trigonometric polynomial approximation to deal with non-parametric settings. Then there's a very interesting paper by Tony Tsai and Mark Lau in 11 that deal with L1 norm estimation and realize that it's going to be really nice, important to replace trigonometric polynomial by polynomial. And later, after we submit our work, we realized Yihong and student Peng Kun independently realized the idea-based polynomial approximation to the entropy problem and devised a really nice technique in the lower bound, which he has just explained. But there's something more to be said. What we showed is also something that this methodology essentially has very deep root in the statistical methodology. And actually, it's a duality with shrinkage. And here, many experts on non-parametric estimation. In short, it means that the shrinkage is designed to reduce the variance. And our methodology is designed to reduce the bias. So whenever you have something in practice, either want to reduce bias or you want to reduce variance. Now you have both methodologies. Now here are some mathematical results. We don't have time to discuss too many details. So F alpha, remember, is this. And here is the L2 rates of MLE for all classes of functional we considered. Hopefully you still remember the first one, this entropy we showed before. There are two terms. Whenever there are two terms, the first term corresponds to a squared bias, second term corresponds to the variance. And we can see that we actually obtained both upper lower bounds of this. So it's an exact characterization of maximum rates of MLE. And you can easily see that when alpha is larger than 1, actually the rate does not depend on S. So basically means really easy to estimate. But now we ask, what's the minimax rate? How does minimax improve over MLE? By how much? We think it's this. So you can just see that for the maximum rates of MLE, usually only bias is dominating. You pick out the dominating term, and you replace that n with n times log n. You replace that n with n times log n. You replace that n with n times log n. You replace that n with n times log n. Here you cannot do because 1 over n is already the best. Even s is 1, so you can never do anything. This is already the best. But actually, after you take the log, if you estimate linear entropy, you still need to replace n with n times log n. So here's our methodology. We think we've discovered a very interesting phenomenon we call effective sample size enlargement. It means that for a very large class of problems, the performance of the minimax rate optimum estimator with n samples, essentially that with MLE with n times log n sample, is precisely a logarithmic enlargement. We can also talk about these things in the sample complexity perspective, which is more common in CS community. For entropy, MLE achieves S, and the optimal S over log S, first shown by valiant. F alpha is S1 over alpha, which actually you think alpha is less than 1. So S1 over alpha is actually super linear. It's really hard to do. And here, what you can actually do is to slightly improve that. You have logarithmic factor. Alpha larger than 1, everything does not depend on S. So it's actually a lossy compression of our general results. Okay. Then we would like to decide more about the entropy estimator, because probably it's something that people want to use in practice. First of all, we emphasize just one realization of general methodology, whose generality we'll still discuss later, because we found this problem very fascinating and very difficult. And we also achieved the minimax rates. And we also need to emphasize agnostic to the knowledge of S. So it's interesting. One may think that you need to first know the knowledge of S to estimate entropy, but actually we show it's not necessary. So basically, by estimating knowledge of S, the support sets, as Yihong showed, is a very difficult question. But actually, for the entropy estimation, it's easy because you don't need to do that difficult part. And also easily implementable. Recall that the only non-trivial computation we're going to do is a best polynomial approximation with order log n, which grows really slowly. We use the following nice software developed by Nick Trevathan's group in Oxford University. Then they compute the 500 order with half a second. And in empirical performance, we have outperformed with every available entropy estimator, which are really a lot in the literature. And our code to be released this week, but now you can send an email and we can send you the code. You can play with that. But however, after we show this to some statisticians, we usually get many constructive criticism, which we really appreciate. But this is that we may not use the estimator, unless you prove it's adaptive. And we, what does that mean? What do you mean by you prove it's adaptive? Yeah, let me give you this example. So what you have shown? What you have shown to me is that the maximum risk of your estimator is nearly the same of the minimax risk over all estimators. But I do really think you take the worst case over all P. Does not make any sense. Why? Usually you say, oh, there are applications where S is large. However, usually one case S is large is in language modeling. Let's consider Chinese language. Chinese language already knows that the available characters at least 80K, really large number. However, if you consider an author's work, are their distribution on their character really like worst case over all possible distributions supporting 80K? No. The most frequently used symbol at most 5K. So basically, you actually know something, the distribution, his style, but actually you don't know exactly. So there's what about I do the following? Suppose I already know a priori, my entropy is upper bounded by h, which is a small number, which is much, much smaller than log s. I already know it. And what I want is that you construct me an estimator such that your maximum risk searching over this set, which is a set of distributions supporting on S elements and also whose entropy is very small. I want the worst case over that set to be similar to the minimax risk over that set, which means that suppose I already know the p's in that set, I design the best estimator. So basically, I want an estimator of doing that. But here, when we still ask a question, but I don't know this h, right? In general, I may have something, but I don't know exactly. Probably I take the worst case, then h is still log s. But they ask a question. Can the estimator satisfy all the requirements, all of these, for all s and all h without knowing any s, without knowing h? Is that really possible? We found this a really big challenge because it means that it's really not clear whether we can really do it. But we like challenges. So we showed it is adaptive. So recently we characterized the minimax risk of estimation of entropy if you take a supremum over that set for any h. And we show that they are essentially in any set, in any region, and just up to a universal constant. And then the first part is very similar to what we had before. The second part is roughly satisfied. But it's nice to see the corollary. They are slightly confusing. It's hard to interpret. I need to agree. What's the corollary? We imply that if epsilon is at least h over log s, which might be very small. Remember that we are considering a case that the h is very, very small compared to log s. Then it requires n as 1 minus epsilon over h samples to achieve the root mean square error epsilon. But let's consider, suppose because h over log s is very small, I take h to be a constant forever. For example, epsilon also a constant. What is 1 minus epsilon over h? It's 1 minus delta. So basically here the number of samples I need is no longer a logarithmic improvement over s. It's s1 minus delta, which is very, very small. So basically it means that if I give you a prior knowledge of the entropy is upper bounded by small h, it really helps a lot. But then you may wonder, what does MLE mean? Probably MLE still requires s. Actually it's not. The MLE still requires slightly more than that, still a slightly logarithmic factor. So you see, oh really? Then in this case, if I give you the upper bound that true entropy is no more than h, even the MLE can be easily sublinear, because this time it's sublinear, it's just a logarithmic factor. So they immediately say that here, still the log n to n times log n for phenomenon is still true. We found this very intriguing because this is already no longer a question we investigated before, but this general phenomenon still holds true, which is really hard to understand. But we found that we think this kind of phenomenon is going to be more popular and more general than what we investigated. However, then we discussed all of these results with some pure mathematicians. They also raised some constructive criticism. They feel that, oh, kind of cool. However, is that really general? I want general. What does general mean? It means that all the functional you have considered, you have one discontinuous or non-differential point, only 1 point. For 1 point, I understand your methodology. Your methodology seems to say that you cover the 1 point by interval, but it's 1D interval. For sure, I know that. Can you give me something is not differential, not at 1 point? Then we consider this example. L1 distance. This L1 distance, the non-differential point is a whole line. Because you think of this as a bivariate function, xy, the point that is not differential is a whole line x equals to y. Then here also need to mention recent breakthrough by Riley and Valiant. They show that optimal scaling is s over log s, which means that if you sample n times from p, sample n times from q, the number of samples needed to estimate this guy is s over log s. However, there is still some small catch, which is only shown to be optimal when n is not really bigger than s. Then, but we want something more. What about n is slightly larger? I want still this to be optimal. But this, we apply our general methodology and we solved it. We show that minimax L2 rates is s over n log n, where MLE is s over n. Exactly, n still be enlarged to n times log n. And we show that the construction in VV cannot achieve this when it's larger than s. So basically, it's not because they didn't analyze, it's because it's by definition in construction cannot really do it. But this is very complicated. Because currently the non-smooth region is no longer 1 point. It's not very clear that you use one interval to cover it. But how to cover a line? You may think probably I use a small square. I cover at the really boundary, cover square, cover this, or I use a band to cover this whole line, or I use some other shape. We don't have time to discuss our result, but we need to share with you some bad news. The bad news that you may think, oh, we still use idea of best polynomial approximation. In 2D, it's not unique. Until now, there's no efficient algorithm to compute it. And also, that when you still think, oh, I don't need a really bad polynomial, I just need a polynomial whose approximation property is quite good, it's also bad news. I can give you some polynomial achieves best polynomial approximation rate, but cannot be used. And also, all the non-smooth region construction idea in this all fail. It's very disappointing. So the solution, you might get some hint from our paper or wait for our soon to be finished paper. And later, I don't have time, but I want to show you one example. So some people also ask us that we don't really care logarithm improvement. It seems still cool in theory, but it doesn't really make any sense in practice. We want to show you actually it's not the case because we didn't talk about the constants. We take the sequence n is 2s over log s because we know for entropy estimation, s over log s is the threshold, is the right scaling. We take this s equally sampled from 10 to 2 to 10 to 7. For each n s, sample 20 times from uniform distribution. They really give a sense a little bit s over n. So actually, it means really big. It means you really in the undersampled region. S is very big compared to n. Here's the performance. As last plot I'm going to show. You can see that s over n is the 2 over 8. It's really big. The MLE is really, really bad. Here at the entropy, here at this point is roughly 14. MLE achieves the mean square error of 4.5 hours is essentially 0. So there's another application in machine learning that I cannot talk about, which also significant improvement, 8-fold improvement in learning tree graphical models. And also, we also didn't have to talk about many other more stuff. For example, we didn't say how you analyze the bias of MLE, which also was not known before. And we need to connect this with another field of approximation theory studied over 100 years. These are why bootstrap and jackknife fail, and multivariate settings, non-parametric settings, non-IID settings, and all who apply this. Some hindsight, so perhaps we're going to skip this. There's some related work, really nice, inspiring pioneers that we suggest everyone to read. And this also later, he mentioned we're going to talk about this work. Then it's some of our work. First one is main work. Second one is analyze MLE. This is an application. This is some divergence. It's an adaptive estimation. This shows Dirichlet doesn't work. This gives the general methodology of analyzing Taylor series, bootstrap, and jackknife. And this answers one question that we'll take once we discussed on how to analyze the gap of Jensen inequality. Thank you very much.